Usually I close that. Just about there. Welcome back, everyone. And it's official. We can start. Welcome back. Well, for today's class, our goal is to move forward in these sections here. But first and foremost, we can always have an unofficial review day, like we were mentioning on Monday and Tuesday of this week. Our second exam runs through these sections right here. And just to give you a rundown of what's going on with those sections, from 7.7, that one's approximate integration. So it's either Simpsons or the trapezoid rules. I wrote the exam already, but I don't have a very big memory for this. I forget which one I asked, but like I mentioned before, this is pretty much randomized. I use a digital randomizer just to decide between the two. Big hint though is if it's Simpsons, probably it's going to be trapezoids on the final. And if it's trapezoids, probably Simpsons on the final. Sometimes I mix it up like that going to the next exam. Then for 7.8, you're dealing with a type 1 or type 2. Same comment as the first problem on there. I'm just going to randomize one or the other. So you're going to do a full problem, either as a type 1 or as a type 2. And another setup for a type 1 and 2. So I'm only going to ask you to do the full problem on one or the either. Then I'm going to ask another question where I just have two integrals. You have to decide, how do you set up the limit? Is it a type 1 where t goes to infinity? And where do you replace, upper or lower bound? Or is it going to be a type 2 where you say t goes to like 3 from the left or above, something like that? You'd only do the setup and then just stop right there. The instructions will say with like caps and bold, set up the integral with the limit statement and then just stop. So a full problem and then kind of a concept problem right after. Then what else do we have going on here? 8.1, 8.2, that's like a block where the problems are very, very similar. I'm either going to ask length or surface area. So one or the other on there. I feel like it's just too long of an exam if I try to make you integrate both of those. Because of 8.3 and 8.3, we'll do a centroid where we have to integrate, where we'll have to find the area, find the x bar coordinate by the y bar coordinate, doing integration. That one can be a long problem, but on an exam, I try to select an integration problem where it doesn't get too convoluted. It's more about knowing the main concepts, how to work through the formula and generate the result. And then the last bit's on differential equations, which sounds scary, but not too bad really, because think of what we did in 9.1. That was just introducing differential equations. And the main thing that we actually did there was just take an equation, a function, and check if it's a solution or not. So that's the main concept I'm going to go for on the exam, checking if y equals f of x, whatever the function I give you, is a solution to whatever the differential equation is. And then the last two we've mentioned before, this is kind of like a block that goes together, but this will be two more questions. One question on a separable, another question on first order linear, where the integrating factor I of x equals e to the integral of the p of x function has a strong chance of showing up. So this is pretty much the organization of the exam. And well, aside from all that, best way to really study for the exam, like we mentioned, have this pulled up and ready to go. Make sure you're caught up on these homework exercises today, or not today, but this weekend is going to be a big grading weekend for me. So if you're working on solving these and questions come up, don't hesitate to reach out. Standing offer is, this is your math work and you're stuck somewhere. Take a picture of it, scan it, send it to my ISU email address, and I'll use these digital tools like you're seeing here to work with you, mark it up, see if I can offer some advice on going forward. Well, this is the best way to study for the exam. Just be caught up on your homework. If you're already caught up, take a look into the feedback, make sure you understand it. Then you might want to go through these 3 different versions. The real exam is most similar to either version 1 or version 2. They're meant to be directly similar to each other. And if you want challenging problems, that's the last one down below. Well, just so that we don't lose this information, let me open up a new file called, the information's still there on the YouTube video, but that's annoying to dig out. Let's call this Exam 2 Discussion. And this will be our first thing to throw into there. Once I get these windows working, there we go. So those are first thing we're going to discuss on the exam. I'm going to save this file and probably upload it right here after the class is over, so you can reference it again if you like. But at this point, I'm turning it all over to you folks. In class and on Zoom, what kind of questions about exam 2 would you all like to discuss? Yeah, go ahead.
I would like to,
Oh, you're good. We'll take your question and then we'll go to Catherine's question right after.
Okay, is there gonna be any question from 7.7 that is gonna involve a graph, like using Simpsons for a graph? Or is it all just gonna be, you get what I'm saying?
I do get what you're saying. Yeah, I believe the question I asked, dang, I have a bad memory on that. I would say we should probably be prepared for either. It could be a graph, but I'm kind of thinking it's more likely going to be a function actually. So I think that'd be what we ought to be prepared for. But just in case, let's say for the first question in 7.8, be prepared for either a function, say I might say y equals, or f of x equals, or let's say the integral from a to b f of x dx, something like this to be approximated, maybe by Simpson's rule, and I'll have to say how many subintervals there. So it could look like that. Or this problem. This is a good problem because it's an application, but I have to be totally upfront and honest. I don't really like it because of the unit problem on there. And the way I handled the units wasn't even ideal when I thought about it. The best way to deal with the units on this problem, that's the wrong section. Let me try again. On this problem was I shouldn't have converted this axis unit. I should have just converted the delta t unit, and that would have been way easier to get through. So there might be a problem like this one, but I'm going to minimize the context. I would probably just focus more on the graph, no unit changes. But I honestly forget what I put on as the official problem. We ought to be prepared for either one. This would have been a way harder one. And let me put it down here. Or for a problem like that one. Other questions about that so far?
yeah, I was wondering if we could go over in the version 2 of the exam, section 7.8, number 19.
Yeah, absolutely. That would be a good one to go with their discussion so far here. So second version, number 19. Let me take a look. That's example down here further. Oh, there's that graph right there. That if there is a graph on the exam, it's probably going to be a little bit more like this one, was what I was trying to convey. Let me throw this in there just as a side thought. This is just a scary looking one, I'd say. Great application, but not the funnest problem to get through on an exam setting. And oh geez, you said number 19, was that 7.8?
7.8, yes.
Oh, gotcha. For some reason, I got mixed up. It was 7.7. Let's give this one a try. X e to the negative x squared from negative to positive infinity. Thanks for suggesting that one. That is a great one for what's a technical section already, improper integrals. And this is like a extra difficult improper integral because what makes it improper is in two spots. Let me just get some extra white space here. Problem like this one, we need to start off by first looking into the limits. We can say this is limit t goes into negative infinity. So go from t to 0, xe negative x squared dx plus the limit as t goes to positive infinity. Match up the value you picked here. Oftentimes we pick a 0. We need some better information to pick something else. Go up to t, xe to the negative x squared dx. So that would be my step 1 on this kind of problem. And when I mentioned at the start of the exam, another setup for type 1, type 2 improper integrals, this is what I mean. That would be the setup. If this was a setup problem, you would just stop right at that step. Thanks for mentioning that, Kevin. And that's a great strategy as well for anyone else in Zoom. Don't hesitate to throw out messages because this way we can just kind of load them in and scroll through the document. So appreciate that question there. And now next thing we have to do on this one is just move through the integration. This goes kind of smoothly if we take an additional step and just integrate xe negative x squared dx right away. Let's find our antiderivative to handle both. Now it's an improper integral. We can use u substitution on this thing. Let's make all of that our u. So u is negative x squared. Du would be negative 2x dx. We've got the x and the dx, so this suggests divide by negative 2. Negative 1/2 du x dx. So back over here, we re-express the integral. Let's pull out the negative 1/2 outside the integral, if you prefer. You don't have to. Then by doing that, the x dx part we see here is just the negative 1/2 already outside du. Inside is just e to the power u. So altogether, we now have, let's see here, negative 1/2 e to the power of u plus a constant. So this turns into negative 1/2 e to the power of negative x squared plus that same constant. So we've got an antiderivative. Now we can look into either one of these and see what happens. But we did make one comment when we were doing this for the first time back in the day. We said, even if this one converges, that information is useless to us if we find out that the other one diverges. So what we want to do as well on this problem is ask ourselves the question, which one looks like it would diverge? Well, hang on. I bet you they both converge now that I'm looking at really close. That negative sign right there is powerful together with the power 2, right? It means whatever your direction you're going, even in negative infinity, this is a positive quantity. And so you're dealing with the exponential going like this. Each time, no matter which direction you're going, it's dampening down like that. Actually, let's go like this to really show it with a power 2 on there. That's essentially what our function looks like. It doesn't matter if you threw an x on there. I bet you we have convergence on both. And due to that, the total sum looks like it ought to be 0. Well, let's give this a try. We can say and take limit. Let's actually code these up a little bit so we know which one we're talking about. Let's call this I1. Let's call this one I2. Now for I1, we can write it's this limit right here for sure. Let's write it first. Limit t goes to negative infinity. Next thing we'd want to do is get the antiderivative for all this. But we've already done it. It's right here. We leave off the plus c because we're going to also evaluate the integral. Here's the antiderivative, -1/2 e negative x squared. Evaluate it from t to 0. So next step, we need to do the evaluation. This is what we would get. -1/2 is a constant. It can move outside of the evaluation block and even to the left of the limit as well. And that's a good strategy just because it means we're not having to pay attention to as much stuff inside here where the limit operation really happens. We plug in 0 into this. E to the power of 0 is a 1, so we just get -1/2 minus, I don't think I need a parenthesis there. Let me undo that. Plug in t, and we get minus, actually, do you want another parenthesis? No, hang on. I think I'm kind of confusing myself on this. When I move that -1/2 out to the front, I think it caused me more harm than good. Now I'm looking at it still right there and getting just a little bit mixed up on the evaluation. Let me back off a step and just do it this way. Leaving it right there, the evaluation would be limit t goes to -infinity. Sorry for the second thoughts on how to write this out. Plug 0 into here, and we get just the -1/2 minus -1/2. Now plug in t inside here, e to the negative t squared. Okay, that looks a little bit better. I factored out my -1/2 on the left, but then I kept on looking at that part right there. Better advice is if you pull -1/2 off to the left, you should rewrite a whole new step, which takes away all the extra speed we've gotten from pulling it out, I'd say. Now, as t goes to -infinity, this right here is going to 0 altogether. That's because of the power 2 and the negative sign. Again, the picture on this is not that. This graph, even as you go to -infinity, that whole thing is going to 0 really, really rapidly. So the sign here doesn't matter due to the power 2. That negative sign is the only thing that matters. Goes to 0 in the limit. That means the value of this entire limit is just -1/2. So that's I1 done. Next, we do I2. But any questions at the moment with solving this one so far? Okay, so for I2, take limit as t goes to now +infinity, same exact antiderivative inherited from that line, -1/2 e to the negative x squared. There is a change though, we're integrating from 0 to t, so change the limits of integration in this way. But one thing you can now think about is, do you really have to do this limit? I mean, really, if you change the limits of integration that way, that's kind of like changing the limits of integration up here. You could take this, just as a side thought for an alternate way to compute, if this resonates with you, you can take this, let's move it up to the next page, switch the limits of integration, and you would get negative limit t goes to infinity, t to 0, x, e negative x squared, dx. And then if you did that, we just solved that problem. We found it equals -1/2. Include the extra negative sign, and now it's +1/2 for that entire evaluation. This doesn't always work. There's just a lot of symmetry in this particular problem making it work. So that's one way to do it. If we didn't have that special feature, we'd have to run through this limit. So let's just finish this out. Limit t goes to +infinity now. Plugging t here gives us -1/2 e to the negative t squared minus -1/2. So that's for plugging in 0. And the limit is exactly the same. Even though the direction changed, we still have that this is going to a negative t squared altogether. So as t gets larger and larger, the whole thing is going to 0. All that's behind is -1/2 for +1/2. And so now we can take this longer conclusion. Therefore, the integral from -infinity to +infinity, x e negative x squared dx is -1/2 plus 1/2 comes out as a 0, so we can give an ultimate conclusion of converges. Then at that step, we're done with this one here. Any questions at all, folks? Finalizing this one. Okay, looks like so far we've got one additional question. Let's look into section 8.3, problem number 30. And, oh, that's two additional questions. Kevin has supplied us with some good stuff here. 9.3, problem number 7. Let's take a look into both. So starting in 8.3, let me see here. Getting kind of mixed up on my notes. 8.3, problem 30. Would that be, which version does that sound like? Not this version. This one doesn't go up to problem 30. Would that be in the homework, 8.330? Possibly. Let's take a look into that. No, you did say that from homework, and 9.37. I should just read that sentence right. Thanks, Kevin. Let me look into that. 8.3. Problem 30. Good choice. This one is a confusing looking one. Centroid for the region bounded by two curves, not much more information given. Let's drop this in right here. And you know, it is tempting to pull up Desmos on these, but let's pretend this is a real exam. I'm going to pull up Desmos just once to show what would be provided on a real exam. I will give you the plot of both of these. It will go y equals 2 minus x squared, y equals x. And so this is probably something you would see on the real exam. Let me just square out this window a little bit better. Okay. And there we go. Now it looks a little bit more like a real exam question. Oh, one new message. Weird. Didn't know where it went. Anyways, back to this one. So here, this is kind of an interesting way to provide the information. Algebraically, we can deduce where the points of intersection are, but you might be able to just read it from the graph that I provide on the real exam as well. Looks like we're going from -2 to +1. It's kind of a cop-out to just say that, citing it out of the graph, right? Because we know these graphs can be extremely deceptive. So if you really want to verify that, just take 2 minus x squared, set it equal to x. Let's solve this polynomial equation, move all terms to the right-hand side. 0 equals x squared plus x minus 2. Factor that thing. Let's go x plus 2, x minus 1. And then it solves as x equals -2, +1. So that's the -2 we see right here. And the +1 we see intersecting way up here. Now it informs us that when we integrate, this is from x equals -2 to x equals +1 on each and every integral that we do. And this is a really good review question because there are 3 integrals we have to do. Step 1 is to find the area of this region right here. And just for the fun of it, let's also try to estimate the centroid of this region. So here's the dot. Let me know if you would agree with this. I want to put it where the most of the mass would be if we really built this out. I would guess about there personally. I don't know if I'm too high or to the right though. Anyone suggest an edit to this? Would you move it in any direction from here? About here. Maybe down a little bit further, sort of around there. Yeah, I would agree. It looks like I was kind of heavy-handed throwing it too far up there. Maybe about right there should be where the centroid is. You don't have to do that on the real exam, but the point of doing this here and now is when you get your answer, if your answer is way off from what you're expecting just by looking at the diagram, that's great information. It tells you you'll have the opportunity to potentially come back and correct a mistake. The other piece of advice on a real exam is never do this. If you know your answer is right, don't delete the whole page by erasing everything. I might not be able to see your work, and you might run out of time to come back to it. So even if your work is wrong, only erase it if you know you've got the time to fill in the correction. So step one, get the area. There's two curves here, so let's start saying which is which. The one that has a curvature is the polynomial, y equals 2 minus x squared. The linear one is y equals x. So we can say area itself is going to be an integral from, let's see if we can color code these to help out just a bit better. Go from -2 to +1. We take the upper function first, 2 minus x squared. Subtract from it the lower function, x. And if we subtracted incorrectly, we would get a negative area. That'd be our indication to switch them around, more critically in the formulas down below especially. So next, let's say we're integrating from -2 to +1 of negative x squared minus x plus 2. I guess I didn't achieve much there, but at least it's kind of in order here. And I'm going to carry my area clear over here to save space. Antiderivative to all this is now -1/3 x cubed minus 1/2 x squared plus 2x. We take all of that, evaluate from -2 to +1. So at +1, we get -1/3 minus 1/2 plus 2. At -2, this will be -8 divided by -3, 8/3. This is going to be +4 divided by -2, -2. And this will be a -4. Provided my numbers didn't go sideways. Let me know if they look a little bit odd so far. Then from here on out, if this is an exam problem, probably what a lot of people are going to want to do is throw this into a calculator. So this is a good moment to remind ourselves, don't forget your calculator, and thanks for the 9/2. That saves us some good time on this one. So 9/2, and we're ready to go. If you put in 4.5, that's good as well. It's exact either way. Next step, x bar. First thing you'd want to do is just write down the formula, especially when you're studying this. It's reciprocal of area, integrate from -2 to 1, x, and ordinarily be f of x, but this is a harder question. There's two functions now. We'll go, this is the f of x function, g of x function, writing that in since the formula is indicated this way, f of x minus g of x. Dx. So next integral to run through. Let's plug in the information for f of x gx, as well as 1 over area is just a reciprocal of 9/2, so 2/9. Integrate from -2 to +1, x times the group, f of x, 2 minus x squared, minus g of x, which is the x there, dx, and now just another integral. Nice thing about these integrals is that they're not too crazy. We're not doing a trigonometric substitution in the middle of all this. Mainly the idea is to focus purely on the concept of the centroid itself. So distributing x inside, I'll get -x cubed minus x squared plus 2x. Practically what we got up here, but practically what we got up here, wrong one, but just to a higher degree. So now this is 2/9. From over here, we pick up -1/4, x power 4 minus 1/3, x power 3 plus x squared. And we're doing this, forgot to specify over here, from -2 to 1. So now it's 2/9. Plugging in a 1 is giving us -1/4 minus 1/3 plus 1. Now at -2, this is getting harder as we go. Let's see. That is going to be a +16 divided by a -4. Sounds like a -2. Now that's -8 divided by 3, so +8/3, plus 4. And then all that happens to go to the calculator next. Anyone happen to have that one so far?
Fully multiplied out, it would just be negative 0.5. If it was a y bar.
This one is the X bar. Sorry, say again? 0.4, awesome.
With that 2 multiplied in.
0.4 times
No, right, like.
with it
all
included,
that,
gotcha. Awesome, thanks for that. That saves us some time on just punching this in. So, and that is right in spec with what we were saying here. Should be about in that line. Now, one more, Y bar. Running out of space pretty quickly on this. Formula for Y bar is reciprocal of area, go from -2 to +1, throw in an extra half factor of a half. And this part is legitimately confusing. Watch out for this step. You go f of x squared minus g of x squared dx. But the critical thing about these powers is not squared right there, which would mean we have 3 terms altogether. We're just squaring the first term and the last term. It's really easy to miss because our training in algebra is we say a plus b squared is to write out a squared plus 2ab plus b squared. And so this might call us back on that pattern, but it's a mispattern this time. So I have color coded what f of x and g of x here is in green and blue. Let's write in. This is reciprocal of area again, so 2/9. Multiplies the 1/2 pulled outside of the integrand. Integrate from -2 to +1. If we're squaring f of x right here, it means we're squaring 2 minus x squared. 2 minus x squared. Squared is how we would write that in. Minus the g of x squared. G of x is just x, so that was not bad, but let me write out this way to just convey something is getting squared from the prior step. Dx. And now we have to run through this one right here. Might not be a bad idea to do this work on the margin. So 2 minus x squared minus x squared.
I didn't make a mistake, the top one was negative 0.5.
Oh, this one right here?
Yeah.
You know, I should have noticed that because I should have noticed that's in the negative
I
region,
don't
right?
know why I
Yeah.
did it.
It looked right at the first. Thanks for mentioning that. Negative 0.5. Actually, from grading these, that looks familiar. I think I'm starting to remember that one.
The 2 on the bottom.
The
For
negative
the dx bar.
right over that one right here?
Yeah.
That one was a -4. Gotcha. That would have been from putting, oh, I see. Yeah, that was like a positive 16 and 4 goes in there. Yeah, that should have been a 4. Not sure why I thought of 2 at that moment. That was a hard one to see. Thanks for those corrections so far. And now at the moment, just a little bit more algebra and we're on our way. Expanding this using that idea above, that's kind of convenient, is 4 minus 4x squared plus x power 4. Then we go minus x squared. So altogether, our integrand is going to be, let's see, x power 4 minus 5x squared plus 4. Let me double check my algebra. Yeah, that looks about right. So all that goes right over here. We are now dealing with the 9th. Integrate from -2 to +1 of x power 4 minus 5x squared plus 4. One last integral to survive, and we've got the centroid of this thing. So this one is a 9th. A 5th x power 5 minus 5/3 x cubed plus 4x. This is going from -2 to +1 again. So at the upper limit 1, we'll take a 5th minus 5/3 plus 4. Now, tricky one, power 5 with a -2. Let's see, 2, 4, 8, 16. -32 on that one. This is going to be -8 divided by -5/3. This is getting kind of rough to calculate in your head. Let me just write it in more cleanly this way. And finally, -8. That's a lot of constants, but throw all of this into the calculator, and what should I expect? A half? Maybe. I'm thinking this looks like a half. Only way to be sure is throw it in. So here we go, 1/2. 1/5 minus 5/3. It comes out as a 0.4. Awesome. Plus 4 minus -32/5 minus 5/3 times -8. We're going for, I'm getting a 1.8 on that. Oh, 2/9. What did I do here? It looks like that's a miscopy actually on the notes, right? So that should have been, there's a cancellation here, so a 1/9. So these should have been ninths down below. One comment I do want to make about a real exam question though is, if you make a mistake right here on the calculator, we're not too worried about that. That's that 0.4 we were expecting. So even if I made a mistake trying to get this into the calculator, let's say I put in like 12 or something, I would mark this incorrect, but then I would look here. If this is right, I'm going to assume, well, you did the calculus fine. You just made maybe simple, your thumb slid and hit a different key. I'd mark that as correct. And I don't think I would even take off points on this kind of situation. That's another comment that we've duplicated all the way back in section, this is worth saying right now. Sorry for the side thought. All the way back in section 7 point, no, not that one, 7.7, I'm getting those confused. In 7.7, another big comment is you do have to write this out on a real exam setting because that's the calculus part. And putting in your calculator is just you determining, is it a reasonable answer? But I take this for full credit on a real exam. That way, you should try to calculate if you have time. But if you made a mistake, that's a calculator mistake, not a calculus mistake. I accept that as full credit. So same kind of concept down here on that one. Well, we got it, folks. That's a kind of a long computation. When I try to write a real exam question on centroids, I try to shorten this up. I solve the problem myself to make sure it doesn't get too long, because I understand this is a long exam already. We don't want one problem to take the whole center stage on it. But any questions at all, folks, on maneuvering through this one? Okay, we've got another question lined up. So 8.3, 30, and 9.37. Let's take a look into that one. So now 9.3, we're dealing with separable differential equations. And on 7, well, that's a good choice. Looks like a lot going on that one. Just an ordinary solve this differential equation style of question. First thing I see that is a big problem is, for solving a separable differential equation, you don't want that y prime there. It's not first order linear because first order linear cannot have a function of y right here. That would make it a nonlinear differential equation. So first step, go e to the power y minus 1 dy dx in place of the y prime equals 2 plus cosine x. In my view, I think this is like the trickiest part of the whole problem. But once you get that lined up, you can now actually begin separating the variables. Notice that the y variables are already in the right spot. We just need to bring dx with everything on the right for the variable x. So this is a one-step maneuver. Multiply both sides by dx, and we have e to the y minus 1 dy equals. Now recall, we have to think of this algebraically. Dx over here is not a derivative, it's part of a differential. So you really need parentheses, 2 plus cosine x, and then the dx. So now we're all set. We didn't show this in the lecture notes because we wanted to show the step-by-step process. But in an exam setting, once you get here, it's cleanly separated. You might as well just throw this on. That's the point. Integrate it right here, once everything is lined up so that the integral makes sense on the left-hand side, and the integral makes sense on the right-hand side, dx lining up with the x variables. Over here on the left, you'll get e power y minus y equals, on the right, it's 2x plus sine x plus a constant. And now, this is the one that we mentioned in the notes, or I believe in the homework exercise write-up, leave in implicit form. If these kind of problems occur on a real exam setting, I bake it into the instructions. I'll say, leave your answer in implicit form. And that's an indication to you that the answer is probably going to involve an interesting combination of the variable y, not friendly to solve. This is the best format for the answer at this point. But any questions at all, folks, on that problem 7? Okay, well, I'll return it back to the class. For our next question, what would you all like to take a look at to next? And thank you again, Kevin. Those were great questions to take a look at.
I wouldn't mind taking another look at another one from 7.8.
Gotcha, absolutely. We had from the class 8.2, number 11, and from Catherine, you said another from 7.8. Is that correct?
Yeah, maybe 29.
Gotcha. So suggestion number 29. Okay, we've got a couple problems lined in. Let's start with this one here. 8.211. Trying to remember what was 8.2. Surface areas. So here we go. And yeah, good memory on that. So we want to find the exact area of the surface rotating this about x-axis. Let me close that. That's can possibly free up some performance on Microsoft Word. Okay, so 8.2, doing number 11. Exact area of the surface obtained about rotating the curve about the x-axis. As a real exam question, the moment you get the curve, I'll also supply a graph. So let's throw that on here as well. So this is, y squared equals x plus 1. That's a fun graph from 0 less or equals x less or equals 3. And interesting. Looks like we've got 2 branches of this curve that we're rotating about x-axis. If that's the case, this is the view we can take. Let's just take the top curve, because if we rotate this about the x-axis, due to symmetry, we get this line as well at the same time. So let's grab that bit, make this our graph. This one looks pretty tricky already because of the format of the y variable, y squared equals x plus 1. So now let's write down, what is the surface area formula in this case? S is going to be an integral going from the bounds provided, 0 to 3. And then it's going to be 2 pi, let's pause right there, and consider the direction we rotate. We're rotating this way, then the whole surface might look about like this. Keep in mind, I'm not very good at drawing these, so your imagination is really important right here. Here's the surface. Pick an x value from 0 up to 3. I'll just let my x value be generically this one. Go up to here, and all we need is the height of this right here to get us started. So what would the height be? Sorry, say again? Ordinarily, but looking into this function, Yeah, I'm starting to think that's a good call on this one. Usually when they give it in that format, I'm thinking my integral is going to be a dx, and I'm doing 1 plus dx dy. But I'm starting to agree with you folks. It looks like it's better to reapproach this, take the actual square root like you're suggesting, and do a dy integral instead. I mean, maybe I should, because I said x is going from 0 to 3 rather than from what would have been a 1 to 2 instead. So let's go with that approach. Let's take this. Y is going to be equal to plus or minus the root of x plus 1. If we're focusing on this branch here, we'll take the positive root. So this is going to be y equals f of x equals positive root x plus 1. And so that gives us the radius here, root x plus 1, or the y is going to go in that location, 2 pi y. And then the integral will also involve this factor, 1 plus dy dx squared. So this looks like a way to analyze it. Interesting though, I don't think I solved it this way. I'm wondering what I did when I did it myself personally, but this looks like it should work. Let's keep on going. Next thing I would do after writing down some stuff, some scribbling on the exam, and getting a formula down below here, start working with the elements of the formula. The dy dx means you're differentiating this function. Differentiating a square root means we go 1 over twice that root. And it's a chain rule problem, but we're multiplying by a derivative of x plus 1, which is times 1, so no change there. Next step is to square that whole thing. So dy dx squared is 1 over 4 x plus 1. The root comes off as well. Add 1 to that. Looks like the algebra will certainly get interesting. 1 plus dy dx squared is 1 plus 1 over 4 x plus 1. Now, sometimes you do want to do lots of stuff algebraically to this. Try to get to the point it's something to a power 2. But question first?
Not looking at it, is you have a common denominator, so you just did 4x plus 4 for the 1 over itself.
Yeah.
Because then when you take the square root of it, it cancels out with the square root of the y, if that makes sense.
It does, yeah. So whatever happens here is going to kind of dictate what you want to do over here, absolutely. Let's take those next steps, complete the fraction, and then we're just going to grab the y right here to kill that denominator, like you're saying, essentially. So next step, we have that this 1 plus dy dx squared equals over here 4x plus 1, or 4x plus 4, as you said, plus 1 over 4 x plus 1 gives us 4x plus 5 across the numerator divided by 4 x plus 1. So all of that right there can go into this entire position. That means it looks like we are able to go forward and fully integrate this thing. So doesn't matter if it wasn't the cleanest way. If we found a way, this is the way to do it. But it looks like this might have been the way that our author intended. Now that I'm looking at it a little bit closer, let's take the 2 pi. You don't have to, but you can chuck it out if you prefer. Go to 0 to 3. Y itself is root x plus 1. Then the root, square root in the black is now going to be, well, let's split this up a little bit. For square rooting a fraction, you can just take the root of the numerator, divide by the square root of the denominator, but that even splits up. If you have things multiplied in the denominator, you can take the root of one term, one factor, and the root of the other factor. And this is what you get, 4x plus 5 and 4, and hang on, x plus 1, let me fix that one. They're all there, but we've also split up the square root across those values to help further canceling on the next step. So here's this next step cancellation. Those are gone, and even more, the 2 cancels with the 2 down here from the root of 4. So all we're doing is integrating from 0 to 3, root 4x plus 5 dx. Hey, what's kind of fun that I forgot is that we've got an answer down here. We should be getting that. This doesn't look like too bad of an integral. It's really up to you how you want to integrate this on an exam. But let me show you how I would integrate this. I'd go from 0 to 3, 4x plus 5 to power 1/2. Because this is, oh, thanks for mentioning that. I dropped it somewhere down the line here after that cancellation. Pi goes here and here. Let me highlight that one. That was really hard for me to see. Thanks for spotting it. So now next step, we can take that pi, take the 4x plus 5 with a little bit of space. Antiderivative is one higher than exponent. So that's going to be 3/2. Multiply by the reciprocal of that exponent, 2/3. And to account for the chain rule, multiply by 1/4, nullifying that factor 4 we see above. That's the full antiderivative, and we evaluate from 0 to 3. So let's see what happens to all these constants. This is now pi over 6 officially. Now, if we put a 3 inside here, that's 12 plus 5, so 17, power 3/2. Personally, I'd leave it in this format, but we mentioned before, sometimes the book goes 17 root 17 for something like this. Plug it in 0, and it's just 5 to power 3/2. And that finally gives us the full integral, maybe. Let's see how we did. Yeah, just a different format here for the answer. That's a pretty tough one. It's kind of fun trying these problems again after we solved them weeks or months ago, because now it looks like a totally new problem. I had no idea how I really should have started this one, whether I should have done a dx integral or keep it as a dy integral. Great suggestion, just solve for y, get that upper branch.
Which one, is it a dx or is it a dy?
This one is a dy integral officially.
Okay.
Or,
Why did it change to-
hang on. No, you're right. That is a dx integral. I think I just got mixed up at the end here. It should have officially been dx. An official answer for that is we use that limit of integration. That's the firmer way to tell. Thanks for spotting that other weird switch around there. So should have stayed as a dx integral. If you used it, the function in this format, you will solve it for x. X equals y squared minus 1. And then it's a dy. But if you keep it as a y, now it's a dx, just the normal version. Other questions about this one so far? Okay, definitely these are tough problems. So that's why I'm only going to ask one, either the surface area problem or the arc length problem. So either 8.1 or an 8.2 situation. And for another one to take a look into, thanks for suggesting this one, Catherine. This is another problem on improper integrals, number 29. Sounds like it might be a type 2 one. So great way to round out this review. And 7.8, back to, this was 29, 1 over x. Actually, this one is a type 1. And interesting thought. This is a side thought, so apologies for the side thought. But I want to connect this with what we're currently doing in the course. Convergence of this integral from 1 to infinity, natural log x over x dx, will occur if and only if we have convergence of a series, summation as n goes from 1 to infinity, natural log n over n. So the convergence and divergence of this improper integral is completely connected and equivalent to the convergence or divergence of the series. That's kind of weird. That's the section 11.3, the integral test. And that's one of the major reasons why we are really interested in this type of improper integral. It's really just connecting with more material down the line. Here's how we're going to run this one. We're going to say it's the limit as n runs off to infinity. Excuse me, not n, got my thoughts conflicted. T goes off to infinity. Integrating from 1 to t, natural log x over x dx. And we could take a similar approach to our other improper integral. solve this as an indefinite and then plug the answer back in. Or we could just stay right where we're at and analyze this one right as it sits. Let's go that route so we can see both equivalent versions of approaching this. We're going to evaluate this one right here now. It's a U substitution, right? Anyone see the good choice for U? Yeah, absolutely. The derivative is that 1 over x we see down below. So right away, that should be U. Du is the 1 over x dx. Slight annoyance though, if you integrate right here in the definite improper integral, you also want to change limits of integration possibly, or undo the substitution. Any approach is valid and you get the same answer regardless. So I'll go the route of change limits. X is from 1 to t, but I'm writing it in the same order I see it here. We plug this into the natural logarithm for u, and we now have that u goes from natural log t to natural log 1, which is a 0. So all this information here can be leveraged against that step to say we're integrating, or excuse me, we're taking a limit. That's the major fundamental thought. We're taking a limit as t goes to infinity of the antiderivative of swap limits of integration, go to 0 to natural log t. Didn't change the nature of the problem because if t goes to infinity, so does natural log t, so no real difference there. We have a u and a du. So now there's not too much left in the problem. That's kind of nice. We're now dealing with limit. T goes to infinity of 1/2 u squared. Evaluate all of this from 0 to the natural log of t. Let me throw no, that'd be the same weird mistake I made earlier. Leave that right where it is. Limit as t goes to infinity of, plug in natural log t, and we have 1/2 natural log of t squared. That's kind of problematic because remember, t is going to infinity, which means it's also going into infinity right here. Then it's minus 0. So the natural log goes to infinity as t goes to infinity. Natural log squared goes to infinity even faster. So this whole thing is infinity, which means it diverges. Interesting side thought. It also means summation as we go from 1 to infinity, natural log n over n must diverge as well. That's some weird lag there. But the convergence divergence of the series intricately connected with the convergence or divergence of the integral itself. And I massively offended Microsoft Word. Let me see if it comes back from this. Just in case, I've got a screenshot of the problem we just did. While we're thinking about what's wrong with Microsoft Word, any other questions at the moment? Yeah, those are all really great graphs. I think that's a great question to end on. Or maybe we have some time for more. I forget there's just 10 minutes. But let's add this as well. Important graphs. And that's an excellent direction to go because notice I've been using those kind of graphs all along with these limits. This isn't the first time. We've been citing what the feature of these graphs should look like in order to do these limits in the first place. So here's some hugely important graphs to keep in mind. First, let's put in the exponentials. Then we'll put in the logarithms. So if you have y equals e to the x, graph looks like this. And important features there are that limit as x goes to infinity, e to the x must then be infinity. Limit as x goes to negative infinity of e to the x. There we pick up the horizontal asymptote, which is 0. And then this can change around confusingly. So there's really 4 limits and 2 graphs related to the exponentials. Here's the other one. So this is y equals e power negative x, and associated limits go limit x to infinity, e power negative x. Well, this time we pick up the horizontal asymptote in this direction. It's y equals 0, so the limit is 0. And limit as x goes to negative infinity of e negative x. The negatives here cancel out, and we're going back to infinity now. So that's a hugely important graph. These exponentials come up a lot, but here's the next class of graphs. First, connecting through 1, take this whole graph right here, flip it across the y equals x line, and you have the inverse function, y equals natural log x. Goes like this. And if you multiply that by -1, you get a slightly different graph. I feel like it's less tricky than the association of the negative variable here. It will go like this, but I'm not too sure if the limits would be as valuable, duplicate them twice, because it's a different kind of reflection. So let's maybe state the limit once on this one, and then let me know if you'd like to see the other versions. For this basic graph, the limits would be as x goes to positive infinity, f of x, or let me be more specific, natural log x. This one goes to infinity, even though depending on how you plot it, your graphing utility might make it look like a horizontal asymptote, but it really does blow up to infinity as well. The next limit is limited as x goes to, you can't say negative infinity any longer, and you can't even say 0, not without a correction. You have to go to 0 from the right specifically, or else this limit doesn't exist. So this one becomes negative infinity. We're picking up a vertical asymptote now, and lim x goes to 0 of natural log x is just a full-on, does not exist outright. So that's the next class of graphs, which I'd say are pretty important. There's even more. I mean, you could put down loads and loads of graphs, but there's one more that to me is a pretty big one. It comes up a lot in Calculus 1. It should come up in Calculus 2, but maybe we just had skirted around those questions. So this graph, let me try again. Let's put this maybe on the next line down here, next page. So we have a graph that goes this way, positive pi over 2, negative pi over 2, so 2 horizontal asymptotes. And this one's from trigonometry. Just from seeing the asymptotes, anyone happen to know what graph we're talking about? Yeah, absolutely. Knowing what the arctangent graph looks like, an arctangent does come up in Calculus 1 and Calculus 2. If any limit occurs with y equals arctan x, it's done just strictly through these graphs. So it would be limit as x goes to positive infinity, arctangent x is one asymptote, positive pi over 2. And if you change the direction, you get the other asymptote. Limit as x goes to negative infinity, arctangent, there's a c there in arctangent, x would be negative pi over 2. And so I think that's the major list that I think about on what graphs do I need to know about to help out with limits. This is essentially all the exponentials, not just e to the x, but 7 to the x, 3 to the x, and so on. And this is all the logarithms, not just natural log x, but log base 5 of x, log base 7 of x, and so on. But only one arctangent graph. I think I misspelled arctangent twice. Let me fix that. Well, any other questions so far, folks, about either of these graphs? Any graphs that kind of popped into your head that you feel like is missing here? Okay, well, looks like we're kind of out of questions. Hey, we're on the bottom of the page somehow, but we still have a few more minutes. Any last questions or comments so far? Okay, with our remaining time, we'll go back to our, no, I'm just kidding. That'd be terrible. We can't really get into any many problems at this point. But I just want to leave you with further advice on studying for the exam. When it comes time for studying for exam 2, keep in mind, I'm going to be pretty available working quite a lot on Friday, Saturday morning, and quite a bit on Sunday as well. If you get stuck on the homework or you're working on any of these exam documents, I'm happy to help. Don't hesitate to connect. Oh, sorry, I missed your message. Would you show that? Yeah, absolutely. Natural log is this one right here. Sorry for scrolling through them real fast. But have a great evening, folks. Excellent weekend. Try not to work too hard if you can help it. And I'll see you all on Monday's class. Unless you're in the online section, we don't have class officially. I'll see you all on Wednesday's class. Take care, folks.
Have a good night. Thanks for answering all my questions.
Yep, absolutely. And thanks to all you folks for posing the questions as well. It's actually hard to get these kind of impromptu reviews going. This is only our very first successful one. Thanks for the help.
Yeah, 7.8 was my weakest section, so yeah, I figured I would ask questions.
Awesome. Yep, take care.